Hi. So now we'll instantiate some objects and test some methods. I'll have to do this part without my microphone because I dropped it in water. So hopefully the quality is still the same. So we will create a class called main. And I've already done that, so if you're using IntelliJ or VS Code, I think, maybe Eclipse, you can right-click your SRC folder, create a new class called main. If you don't already have a class called main, or whatever you want to call it, driver or whatever. We will start by instantiating a linked binary tree, so there's probably an error somewhere. A linked binary search tree of type integer. We'll just call it tree points to new linked binary search tree of type integer. So we'll say tree dot add element. We'll add an element. We'll add 5 to the root. Actually, maybe we should. Actually, that's fine. So we'll add element 5. We probably will have some mistakes, so let me just pull up my notes just in case. 1 sec. What do I call this? Best linked binary search tree. We'll open that. So I'll just have it just in case. We probably will get some errors somewhere. So let's say we'll have 5 in the root. We'll add a smaller element, so we'll add 4. And we'll add a bigger element for the right child. So left child should be 4, right child will be 6. And we'll add another level, so we'll say so we have 5. So how does it look? So let's just do I can't do a diagram because I don't have the screen recorder, so I only have a game recorder, the Windows one. So we'll just say we have 5. And then we have, actually I'll do it down here. So then we have 4 left child. Maybe like that, and then we have 6 for the right child. So that gives us 1 child each, and maybe we'll have 2 more. So we'll say, okay, tree dot add element. We'll be doing some rotations and stuff after this. We'll do the decision tree using the list, and we'll create a decision tree and stuff, so that's coming up after this. Then we'll do the heap, and then we'll be done with trees. So here we have 5 as a root, 4 as a left child, 6 as a right child. Then we'll add maybe 2 and 3. So okay, let's say we have 5. So pretend we haven't added these yet, so we have 5. Then we'll be like, okay, we're gonna add 4. So is 4 less than or greater than 5? So 4 is less than 5, so it's gonna go to the left child. Then we want to add 6. Then we'll say, okay, is 6 less than 5 or greater than 5? So it's greater than, and it'll go to the right child. Then here we'll say, okay, we'll add 2. So we'll say, okay, well, is 2 less than or greater than 5? It's less than, so we'll go to 4. And then we'll say, well, we can't add it here. Is it less than 4 or greater than 4? Well, it's less than 4. So it's going to be the left child. So we'll put it here. Maybe here. Or there's fine. Then we'll say, okay, well, we want to add 3 now. So we'll say tree.add element 3. So we'll start at the root again. When we add an element, we start at the root. We'll say, okay, is it less than 5 or greater than 5? So is 3 is less than 5, so we'll approach the next level. So we'll say, okay, is 3 less than 4 or greater than 4? We'll say, okay, it's less than 4. Actually, I wanted this to be a little different. Let's forget that for a sec. Let's change the root to a bigger number. Let's try 11. So we'll say, okay, we're going to add 11. We've added 11. Then we'll add 4. Is 4 less than 11 or greater than? Well, it's less than, so we'll go to the left child. Then we'll add 6. So we'll say, okay, is... that doesn't work either. We'll have to change 6 to something else. Maybe 20. So we'll say, okay, well, we're going to add 20. So is 20 less than 11 or greater than 11? Well, 20 is greater than 11. So we'll put 20 here. Then we'll say, okay, we're going to add 2. So is 2 less than 11 or greater than? It's less than. Then we'll approach the next level and we'll say, okay, is 2, we're adding 2. Yeah, 2. So is 2 less than 4 or greater than 4? It's less than 4. So we'll add it here. We'll pretend that it wasn't added and we'll add it here. Because 2 is less than 4, it's not greater than. If it was greater than 4 but less than 11, it would be 5. If we're adding 5, but we're adding 2, so 2 is just going to go on the left child. Because 2 is less than 4, it's not greater than 4. So if 2 is greater than 4, we put it at the right child, but it's not, so that's fine. So then we're going to say, okay, we want to add 5. So we'll say, okay, is 5 less than 11 or greater than 11? Is 5 less than 11? So we'll say, okay, 11 is the root, is the element we want to add, which is 5. Is it less than 11 or greater than? It's less than 11, so we'll approach this level. Then we'll say, okay, is 4 less than 4? Sorry, is 5 less than 4 or greater than 4? Is 5 less than 4 or greater than 4? Well, 5 is greater than 4, so we'll put it as the right child because it's greater than that number. And if we're searching a tree, right, it's either going to be greater than 11 or it's going to be less than 11 or greater than 11. So we're looking for 5, and we're going to say, okay, well, 5 is less than 11, so it should be on the left side of the tree. And we'll be like, okay, well, is 5 less than 4 or greater than 4? Well, it's greater than 4, so it should be in the right subroot of the left root. So that's where it is. That should be correct. Then let's say, okay, we want to add, let's add 18. So it'll be like tree.add element. We'll add 18. Then we'll say, okay, is 18 less than 11 or greater than? Well, is 18 less than 11 or greater than? It's greater than, so we'll approach this level. Then we'll say, okay, is 18 less than 20 or greater than 20? So it's less than 20. So if the number is less than 20, then we'll put it as a left child. So that's correct. So if we're looking for 18, we're going to say, okay, is 18 less than 11 or greater than? Well, it's greater than, so then it should be in the right child, or the right subroot of the tree. So this is our tree. There's the root, these are the subroots, and these are the leaves and the children. This is the children of the root, or these are the children of the root, these are the leaves. So if we're looking for 18, it's greater than 11, it'll be in the right subroot. Then we'll say, okay, we're at the next level, so is 18 less than 20 or greater than? It's less than, so there you go, we found it. So we'll say, okay, we want to add one more element. We want to add one more element. We'll say, okay, we'll add 30. So we'll say tree.add element 30. We'll say is 30 less than 11 or greater than. We'll say, okay, 30 is greater than 11. So should we add it here? No, we can't because there's already a node here. So we'll say, okay, is 30 less than 20 or greater than? Well, it's greater than. So now we're at a null position, so we're going to add it here because there's an empty spot. So we'll say, okay, we have our tree now. We can't print it. We'll just run it. Save and run. Probably get an error somewhere. I can't see the errors, it's not showing it. Okay, forgot the brackets here. Java else without if. Which one is this? Private T remove element. Is this that's the support method. So let me have a look at that. So private T remove element, let me just make this a little smaller, make that to the left. So okay, we'll say T result, if node is equal to null, throw the exception, else that statement in the if block, else, and then if result points to node element. So if else, I think I doubled it, so it should be result points to node.element, binary tree node of type T, temp points to replacement node. If parent.write is equal to node, parent.write points to temp, else parent.left points to temp. So we have a double line here. You can fix that if you accidentally did it. I apologize for that. It's a lot of code here, so I just trying to type and read. So correct that if you do. Save and run. Where are we now? Binary tree node. What class to read? Link binary search tree. Replacement. So private illegal start of expression. What line does it say? 184. So else if node.left. So if else if node.left. Excuse me, I'm gonna be yawning a lot today. I didn't really sleep that much. We're gonna say node.left is equal to null. And node.right is not equal to null. We should have. Oh, that's fine. So result points to node.right. Missing a bracket here. Override abstract method iterator pre-order in binary tree ADT. Maybe they spelled it wrong compared to the interface. So in order and then pre-order, or whoops, per order. So you can fix that if you also did that. I apologize. I'll just apologize in advance for all the errors. So hopefully we can get it running. Where is this? Link binary tree, return iterator in order. Is that a... Let me check that code too. Where did I even get this code from? That part of it. It's an old assignment, so it's probably in this folder here. This is link binary tree. Is that link binary tree? Yeah, it is link binary tree. Okay. Let me just open my notes up again. So public iterator of type T iterator. That's down at the bottom somewhere. Here we go. So we're missing brackets here, I think, or parentheses. Try that. Does it need a capital I? No, I and O should be right. Missing return statement. Which one is this? This is the methods that we didn't use, so that's right. So that's the linked binary tree get left. Does that get left? Public link binary tree of type T get left. If root is equal to null, throw new exception. Result points. Okay, so we just have to return result, I believe. Return result. Actually, we can just do that above here. Save that and run it again. Okay, this is the remove element public method. So let me go back to that notes, or those notes. Link binary search tree. Best link binary search tree, that's the one. Remove, not the private method. That's the private one. Okay, public T remove element takes T target element. So we should have had else result points to remove element target element. We duck at right parent, 2 brackets, and then outside the else return result. Save that and run it. Yeah, we could be doing this for a while, so apologize for that. I think the other one had like quite a few mistakes. Oh, maybe not. Okay. When I first tested this, like I tested it a day before I made this video just to see if it was working. I literally had like 50 mistakes, so I'm not sure why this one had less. So hopefully it did work. We'll check that by debugging. So we'll go to the main method. We'll put a breakpoint here. We'll click the debug icon and we'll start debugging. I think we're just going to debug the link binary search tree methods because we're using the main methods that we need anyways from link binary tree, minus like the get the num children and stuff. Why is that so small? Oh my god. Can't even see that. And I cannot make it bigger. That's great. I have like a really big screen and this writing's so small, the font. It's wonderful. I think I have like a 26-inch or 27-inch screen. So we'll step into that. We'll step in to, actually no, sorry, the screen's only 25 or 24, but it's pretty big compared to my laptop, but I can't see it. But we'll step in to args. So I think there was a glitch there, so we'll just re-debug it. Maybe not. Okay, so we're in args now. We'll step in. So that's my mistake. We'll step into linked binary search tree. We're instantiating our tree here, so we're going to go to the. It should bring us to the linked binary search tree class. So we'll step in. Now we're in the linked binary search tree class. So okay, so we're here. Let me just close these. List ADT, binary tree ADT, unordered list ADT, exceptions we don't need. ADT, tree node, main, binary tree and linked binary search tree. Okay, so we've instantiated this linked binary search tree of type integer objects named tree. We called it tree. We set it to point to new linked binary search tree of type integer objects. So we've instantiated our object, which is a linked binary search tree. So the compiler is going to say, okay, well, we're going to go into this class, the linked binary search tree class. So we'll step into the class. Then it says, okay, so we're in the constructor now because the constructor sets up the linked binary search tree object, of course. So now it's saying, okay, we're going to call the super reference. So we're going to step in, and that's it. So what does a super reference do? The super reference sets up the super class's instance data and calls the constructor. I forgot the exact definition. If that is not it. But we'll step into the super method, which is going to bring us to the linked binary search tree class, and that is because linked binary search tree of type T extends linked binary tree. So if you don't know inheritance, that just means a linked binary search tree is a linked binary tree, which implements the binary tree ADT, and there's inheritance within that as well, but that's okay. We'll just step in here. So now it has brought us to the linked binary tree class. Here we're at C, public class linked binary tree of type T. So this is like the general class. We may have been able to make it, we may have been able to have made it abstract, but we didn't, so that's okay, because we didn't have any abstract methods either. But you can try that, or we can try after. So here we're creating an empty binary tree. So again, we called main. It brought us, we're instantiating our linked binary search tree object. So we went into our linked binary search tree class to the constructor that is taking no parameters because we did not pass any parameters. So we're going to say, okay, go to our ls or lbst linked binary search tree class and find the constructor with no parameters. So there's two of them only, I think. This one has a parameter, so it's like, okay, well, we're going to take the one without a parameter. So we'll call the super reference, which brings us to the super class. And again, there's no parameters. So we'll say, okay, let's go to the constructor, which of there is 3. We'll go to the constructor that takes no parameters. So we'll say, okay, well, what's our instance data right now? So here we have nothing. Now linked binary tree, we have a root. So once again, every binary tree node object root has an element, a left child, and a right child. a binary tree node left and a binary tree node right object reference variable, in which those object reference variables have their own element, their own left child, and their own right child. So a diagram, I might have to do a diagram for this one just to explain it. So hopefully you can picture that. It's going to be a little hard for me to type that out. Paint probably will work best. We're going to say, okay, well, we have instance data here, and in our linked binary search tree, and within that we have a linked binary tree, or it is a linked binary tree. So we have a root, which is a binary tree node root, and we have a mod count. So let's not worry about mod count. Let's just focus on the root. So we'll say, okay, well, right now it's null because it's not pointing to anything. And here we're gonna just explicitly set it to null. So we'll say, okay, well, we're gonna set root to null, and that's it. We're gonna come back from our linked binary tree class. It's gonna go to that bracket. Then it's gonna, what happened there? Great. Something glitched out here. Can I just drag that there? Still debugging, camera didn't stop. Okay, so we're at, what was I saying? We're here. Okay, so we were here, right? We're here. We're at this bracket. So we got here. We set our root to null. Then we got to this bracket, so it's gonna bounce back to the call after super, right? To this bracket. Then it should bounce back to here, and then continue this line. So we'll go here. Are we here? I'm not sure. I think we're here now. Step in. So yeah, we're here now. Step in, and now we've moved to the next one. So it waited to continue to this line. We can see here we have our tree object because we named it tree, and our tree object contains a linked binary search tree. Right here has a memory location at 952, so the whole tree is being stored at memory location 952. So we'll say, okay, in that tree we have a root, which is pointing to null, and a mod count, which is pointing to 0. So I'm just going to forget about mod count. We don't need to know that right now. We'll just focus on the tree itself. So we'll say, okay, that's done. Our tree object is set up, and we're ready to start adding elements to it. So I hope you understand. So we'll say, okay, we're going to jump into the add element method. 1 sec, I'm just going to have some water. Actually, my water's all the way back there. Great. I'll try to reach it. So I hope you understand so far. Alright. So we'll continue to step into this method. We're going to access our object, our tree object. Then we'll say, okay, well, we want to call our tree object. We're going to access our tree object, use the dot operator to access our add element method, and pass in 11 as parameters. So we'll say, okay, we're going to step in. We're now on the add element method in the linked binary search tree. It has a parameter. It has the parameter 11, so we're going to pass 11 into the parameter for the method. So I think these are actual parameters, and we're going to pass to the formal parameters 11. So it's saying, okay, well, is or if element, so it's our parameter is called element. Excuse me. So here we have 11. Whoops. So we're saying, okay, well, our 11 is called element. 11 is set, or element is set equal to 11. Right here, element is set equal to 11, has its own memory location. Yep, so that's fine. So what we're going to do when we add an element, we're going to have to instantiate a node, but first we're going to check here. If element, which is 11, is an instance of comparable, if element is not an instance of comparable, so that should be false, it is an element of comparable. I think when I first did this, I actually implemented the comparable interface and like set all that up and made them into comparable objects, but I think the integer class already implements comparable, so it should be fine. So it's going to skip that, so it is a it is a comparable element, so we won't have to throw our exception that it's not a non-comparable element. So it gives us an ordering, a natural ordering. So here we're going to perform the cast, so we don't have to do that 3 bracket thing with comparable cast to each line we use. So we'll say, okay, comparable of type T, comparable element points to comparable of type T element. So we're just basically now comparable element points to element. So we're going to access element by calling comparable element. So we'll step into that. So here we can see comparable element points to 11 right here, which is element. So if is empty, so if our tree is empty, we'll step in and it's going to bring us to the linked binary tree method where we have that method. It's going to say, okay, well, returns true if our root is equal to null. Well, our root is equal to null right now, so we can see this root points to null. So we'll step in. So if is empty, it's going to proceed into the brackets because that's true. So now root is we're going to instantiate a node here, and we're going to call it root. So where's our binary tree node? It's up here. Sorry, where's our root node? It's here. So we have our binary tree node stored in our linked. We have our binary tree node named root stored in our linked binary tree that we have through inheritance. So every linked binary search tree has a root, and that root we're going to carry it here, where we have it at this point. It's accessible. You see, it's not in this class, so we can call it, right? So can we underline? And probably not during a compilation. But I think if we hit stop, we can see that it's going to be in that class, so we can check that after. But just remember, we can access that root from here, so that might be a little complicated. We're not even having to use the this, or we could use the this. We don't need to use any dot operators at this point, so it's fine. You can call root like that. But if we wanted to access the binary tree node elements left and right, I think we could use the dot operator. We could say root dot element points to, but instead of doing that, you can encapsulate it using protected or whatever, or private, if that works. And then what we have is getters and setters, so we access all that stuff with getters and setters. So I usually do that, and I don't really explain it, so hopefully you understand. So here we're gonna instantiate a new node. So our binary tree node, it's just an object reference variable, it's empty. So we're gonna say, okay, well, let's instantiate that root to become a real root. So we'll set root to point to new binary tree node of type T. We'll pass in the parameter element, so we'll say, okay, well, that root's gonna hold 11. So that's done. Actually, no, it's not done. So we stepped into that method. Because we're instantiating a binary tree node object, it's saying, okay, well, let's go to that constructor, the binary tree node constructor, because we're setting up an object with a parameter. So which constructor has only one parameter? Is it this one? No. Is it this one? Oh, there is no other one. So it's either this one or this one. So this one has one parameter, so we're going to go with that constructor. So again, root points a new binary tree node of generic type T element. We're going to go into that constructor. And we're going to say OK. Binary tree node. We're going to go to that constructor and say, okay, well, we're going to go to the constructor with one parameter, which takes an element. And we say, okay, well, our element is 11. We've passed that through a few methods. Or through this method, and we're passing it here. So hopefully you understand that. It can be a little confusing. So we'll say, okay, here, root points a new binary tree node element. We go into the constructor. We'll set this dot element, so this instance data here will get set to the parameter element. This dot element points to the parameter element, so that's going to get set to 11. So the instance data for this object, this binary tree node object, the element instance data will get set to 11. All left will get set to null, or it'll stay null, and right will stay null, or set to null. Done. And guess what? We just added our first element, and that's it, because we had if, so if it's either empty or it's not empty. So if there's only two options here, otherwise if it's not comparable. So if the root is empty, we need to root, and that's how we set up the root. Otherwise, this block gets skipped because that would be the element after the root, or any element after the root. So we're done. Congratulations, you added your first tree element. So where are we now? We're at the bottom here. I think we're here. No. Mod count incremented already. Should have. Unless it glitched. Mod count plus plus. Did it not increment? That's weird. Unless it glitched, which I don't. We set mod count to 0. Mod count, no. Is that a mistake on my part? I'm just going to check the notes actually just to see if I missed that. Because mod count, I think it should have incremented. Link binary tree, unless there was a glitch in the textbook. Public link binary tree. Mod count. There is no mod count plus plus. That's strange. We're not using our iterator. Or we should have maybe set mod count equal to 0. Somewhere here. I think there might be a typo in the textbook itself, so let's just stop that. And we'll just set mod count, all of these to mod count is equal to 0. Or actually, we don't even need to do that. Let's protected in mod count is set to 0. Can we say that? Then can we jump back into that method? It's going to give us an error. If not, we'll just leave it because we're not working with the iterators at this time, but should be fine. That's strange though, because I did do a traversal and it did work. Okay, so well, not in this video, but before. So we'll skip that. We'll step in. Mod count set to 0. Wasn't already 0? Skip that. Skip that. Skip that. Skip that. That is so strange. It didn't even increment. Got a glitch on the compiler or what? There's no other explanation for that. You don't really need to worry about it, it's not important for trees. But I'm just wondering why it didn't increment. There's a lot of stuff here. Tree iterator. Let's just not worry about it for now, so we'll just, I swear they've incremented before, they must have. Remove all watches. I haven't updated it yet, but you can't, I don't think you can do that in the new update. So anyways, we'll just continue with that. So we'll add 4, step in. So we can skip that. So we'll cast that, we'll skip that. Well, it's not empty. We'll step in. Returns true if root is equal to null, so we'll sit check, okay, root. It points to a node at 991, which holds 11. Has an element, so remember every root has an element, a left child, and a right child. So every root here has an element, a left child, and a right child, right? That makes sense? So our root for our tree, there's only one root, has an element, a left child, and a right child. So there we go. It's not empty because our root points to a node. We'll step in. Where are we? Okay, so don't worry about that. I think it's a little glitching here, but that's okay. So if it's not is empty, it's not empty because we went to this class, to the isEmpty method somewhere here. Height is empty, so returns true if root is equal to null, so return false. Therefore this statement was false. So if true, then proceed into these statements, but if false, then skip to this bracket. So now we're here, or outside this bracket. So now we're here, else, proceed in. Now we're at this statement, if comparable element, which points to the element as we said, dot compare to root dot get element. So if comparable element, which is 4, dot compare to the root. So comparable element, what are we adding? We're adding the element 4 right here. So we say okay, 4 dot compare to, what's the root dot get element? Well, the root is 11. So is 4 less than 11? It is, so it's true, so it should proceed to the next statement. Because 4, comparable element, you can put a 4 there, dot compare to root dot get element. The root dot get element is 11, is less than 0, so if the left is less than the right, then that should be true. So we should proceed to the next line. Is it going to bring us to some internal method? I guess it is. You can step over that next time, I think, or else we're going to get stuck in there. So we'll say, okay, if root, so we'll take the root. Can I remove these watches? Okay, so root. So we'll say, okay, here's the root, it's 11. So we'll say, okay, if root dot get left, so we'll say, okay, we'll get us the left, let's access the left child. If it equals to null, well, that's true. So step in, get left returns left. It does equal to null, so it's true. And we'll say this dot get root node. I think we could have just said root dot set left, as we did here. what they did a little different. They just said this. They're showing us what they're accessing. They're just saying this linked binary search tree dot get root node dot set left. So I think we could have just done here, because since, see how we did root dot get left. Does that show us binary tree node? So we went here. So we went where were we? Get left. So we right here we went to get left, right? So we could have just said okay, get left, and then now let's just set left. So they just kind of trying to confuse us here. But what we could have done is just said okay, well, root dot set left. Could have just said put here, just put root instead of this. That's all it's saying. So it's saying okay, root set your left child to a new. We have to instantiate a node, because if we're setting a node, we have to make sure it's instantiated, unless it already is. But it's not, so we have to instantiate it. Because we created a node here for the root, and only one for the root. We haven't instantiated any other nodes in here. So now we're going to say, okay, well, let's instantiate a new node and pass in an element. So it's going to take the parameter of binary tree node with one element again. Step in, set left. Did it just skip that? So it might have just skipped that constructor, but all it's doing is it's going here to binary tree node with one element. Or binary tree node, sorry, with one parameter. It's setting up that node. Can we find that node here? Let's just stop that for a sec, apologize, and see if I can find that node before it's instantiated. So click the debugger again. Skip that, step in. Skip that, skip that, okay, step into that. Hasn't brought us anywhere. Should have had a node here, but nothing popped up yet. Now we have our node. So we have a node here. We're calling it node. So we're saying okay, this dot get root node dot set left. So we're just saying root dot set left. That's all it's saying. To a new binary tree node of type T, passing an element. So it's just taking an element. We're just doing an instantiation here. Maybe you could have put a binary tree node of type T. You could have called it something, but this is like a shortcut way, so it works. So now we're in the binary tree node class. So here's our node. We're trying to add 4. So you can see here, new binary tree node of type T, holding an element. Well, what's our element? Our element's 4. We're trying to add 4. So there you go. There's our node at memory location 1021. Has a left and a right child, as we said. Every binary tree node has an element, a left child, and a right child. So now we're saying, okay, we'll set the left of the, where are we? I think we're here. We were here. It's not showing us where we are. So we're here. We're saying, okay, we'll set the root node's left child, right? So the root node's left child, this one, set it to this node right here, holding 4. So left points to node. It's this left. This root. So the root. You could have just said root dot set left, or this dot get root for the so all this dot get root node is saying is this tree object. That's why it's saying this link binary search tree. Well, it did say that before, but this root, the main root, right? We only have one root for this tree. So take this tree, this linked binary search tree, of course, the root in the linked binary search tree. Get root node, that just returns root. We've seen that before. Is it here? Good. Maybe it's in the linked binary tree class. Get root node, get root element, get root node right here. So it just returns the root of the tree. So it's saying, okay, tree, this tree, get the root node for the main tree, and set its left. So there's two ways to do it. So there's this way here, and there's this way here. Whatever works. Personally, I just find this one easy. Root dot get, but doesn't really matter. So here we'll say that. We're back here, so hopefully you get what's going on. We'll point that to there. So now we can see our root here. This binary search tree, I think it's stuck in something. Okay, so this linked binary search tree has a root, and now guess what? Its left child is set to that node. I think it was 1021. I forgot the exact number. Pause the video and see if it is. Either way, it should be. And we've set that to the left child. Where are we now? Should be done to mod count plus plus, which it isn't incrementing. First time it didn't increment. That's weird. So let's just not worry about that. Don't worry about it. Maybe it's a glitch. We have our we have our node set to our left. Wherever left child set. We're done with that. We're gonna add 20, so our tree looks like this. We still have the 11, 4, so left child we're gonna add 20. We just may add, I don't know if we'll add all of them, but we'll add maybe a few more. So we're going to add 20 now to our tree. Sorry, it's going to have some more water because I'm getting a little headache from not sleeping that much. So we're going to add element 20. So we're going to step in. So we have our tree. 11 is the root. 4 is the left child. So we're going to add to the right child now. So it should be the same thing. It's just I'm just going to kind of go through this quickly. So compare to. So if it's not less than. So if comparable element. Let's remove watches here. Which is 20. Dot compared to root dot get element, which is 11. So 20 dot compared to 11 is less than 0. Is that true? No, it's false. So we'll proceed to this one here. It's because either greater than now or equal to. So if root dot get right is equal to null, which it is, we just went through that, so it's doing the same thing on the opposite side. So if root dot get right, which is null, so that's true, take the root, get the root, that's what it's saying, get the root, or access root dot set right, whatever, you can do it either way. Now set its right child, which was pointing to null, to the new node, which is 20. So if we check our root, we'll say, okay, well now we have 11 as a root, 4 as a left child, 20 as a right child, done. Mod count plus plus. So it's going to say now add 2, so we will maybe do 2 more just to show, because it's going to go into that private method now. So it's saying, okay, we're going to add 2. So we added those 3. We're going to add this one now. So it'll say, okay, let's go back into our add element method. Where are we? Right here. So we'll skip that. Skip that. Root is not empty. Skip that. So is the comparable element, which is 2, dot compare to 11 is less than 0. Well, it is. So we'll step in. You can step over so you don't have to go through that integer, the built-in integer class. So we'll say if root.getLeft is equal to null, what is it? Is root. Here's our root. And our variables in our debugger. Is the root.getLeft. So is the root.getLeft child is it equal to null? It's not, so that's false. So we'll try to step in there. Return left 4, so false. We go to this else statement. So it's saying, okay, now call add element with 2 parameters. We'll say, okay, we'll step in. And we'll pass an element which is 2. And we'll use the node, because it takes a node, I think. It takes a node, so we'll call the root dot get left. So it's going to take the 1021 as a parameter. Memory location 1021 for root. So it says root. We're at root dot get left. So it's going to use the node storing 4 as the parameter. So we'll see how that works out. Step in. So now we're in the private support method. Takes 2 parameters. Element 2 and the node holding 4, that's what it says. It's going to perform the cast, we'll skip. So if comparable element, which is 2, dot compare to the node.get element, which is 4, because it was taking root.get left as the parameter. So this dot root dot get left, which is storing 4. So it's saying, okay, well, 2 dot compare to is 2 dot compare to 4. It's trying to compare it to the next subroot to see, okay, well, is it less than or greater than? Well, 2 is less than 4, so comparable element dot compare to. So comparable element, which is 2, dot compare to 4 is less than 0. So it should return -1. So that should be true. We'll step in with the step over. Then we'll say, okay, if node.getLeft is equal to null, so is the node, is the node which is referencing the roots dot get left, so the root dot get left, well, if node dot get left, because it's less than, so it's going to go to the left, so so it's asking, okay, well, is the subroot, which is 4, is its left child null? Well, it is, it's pointing to null. So it's saying, okay, well, we're going to step into that method, or that if statement. It's going to say, okay, well, let's set that node to 2, because that's the spot. It's going to instantiate its node, binary tree node. It didn't really go there. It should have. So it did glitch. Sets left, and now we'll see, okay, well, let's remove all watches. We have this link binary search tree, its root, which is 11, its left child, which is 4. Now its left child has been set to 2, and its right child is null. So it's going to keep doing that. Excuse me, it's going to keep doing that over and over again. That's how the processing works. I mean, we can go through it, but I think you get the idea. we maybe can do not. I don't think we'll skip the right one. So where are we now? Set left. It's done. So it's add element set left. So if then we hit here, this else got skipped and it was done. Now this, we're back here to the normal method, not the support method. It's done with the private support method. Then we'll say OK. We're down here. This is finished, so process is going to continue. We'll continue to that bracket here. Else will get skipped because it's either else, if or else. So this one was executed. This one will get skipped, and we'll go to mod count plus plus. Mod count plus plus will become 3, apparently. Then we'll skip. Then now we're going to be at tree.addElement 5. We're going to add the element 5, so where's that going to go? So we added 2, now we're going to add 5. It's really the same thing, because it's either going to be the left child of 4 or the right child. Then it's either going to be the right child, the left child of 20 or the right child. So that's fine, we can skip these, so we'll just skip. Let's stop that and put a, let's see if it shows anything, so it'll be like system.out.println. We'll print our tree. I don't think it's actually going to show anything, it might. We'll put a break, no, actually that's fine. Let's maybe take that one off, start again, re-debug it. So we'll say okay, we're here, we got our tree. Let's check if the data looks like this internally. So our root's 11, left child is 4, right child is 20, that's correct. Then we'll click the left subroot. We'll say okay, well the element's 4, the left child is 2 of the subroot, and the right child is 5, so that's correct. If we click those, they should be null, the next children. Okay, wait. Root. Then we got the root, and then left child. Left is 2, those are null. Right child is 5, those should be null. Null and null. The leaves are null. Or, not the leaves. Just the nodes below the leaves are null. So we'll just leave it at that. And actually we'll just check the right side of the tree. Where are we? 11. Left is 4, we check that 20 is right. So we should have a left 18 and a right 30. We'll check left if it's null and null, correct, null and null. And the right 30 child, null and null. So that's all correct, it's working, we have our tree working. We'll stop debugging. Actually might take a little break here and come back. How many methods do we have here? Actually, we could maybe just keep going. We're going to be concluding the tree, so I think this is like the fifth or sixth part of the video, so it's 5 or 6 hours. So hopefully you are understanding it. If the video is helping you, if you'd like to see more data structures and free coding stuff or technical analysis of stocks, cryptocurrency, and forex, to learn about technical analysis, then you can subscribe to the channel if you want to. And with the support, I'll be motivated to make more videos, more free stuff. So after that, so thanks for that, and after that we'll just continue with the remove method. So we have the add element, we did those two, we just have the remove one, remove all occurrence replacement. Yeah, we're gonna have to go through all those. That one too. These ones, remove min, remove max, are pretty easy. Let's just try to get the next remove one. So let's say, okay, we want to remove the target element, the first target element. So we'll say, okay, we really just need to do one. We don't really need to do all of them. Hopefully we can enter this whole method with just one. So let's try to remove a bottom element. So let's say, okay, we'll remove 30. Let's actually, okay, let's just see if that printed out, by the way. I don't think it will print any. Oh, it did, okay. Oh yeah, because we did the traversal. We printed them out using a traversal. I think we use an in-order traversal. We can check that by going to link binary tree. ToString. Somewhere is our toString up here. In order. Yeah, we did an in order traversal, so it prints the nodes out in order like that, in ascending order. So okay, we'll go to the main class and we'll say, okay, tree.remove element, and it's gonna take a target element and say, okay, we'll remove 30. We'll remove one of the leaves, and we'll create a breakpoint. We'll save it and debug it. So we have our tree, we just checked it, that's fine, we'll just step into this method. So t result points to null, if is empty, it's not. Parent points to null, another object reference variable. Here's the cast that they do every time, because I didn't do that general cast of that element to the other element. I forgot what we called it, but here we'll do the cast. So we'll say, okay, if comparable of type t target element. So target element is 30 dot equals the root dot element, which is 11. So it's checking, okay, well, is element the first node? Is it the root? What happens if we step in? It's not, right? Does 30 equal 11? That's false. We'll see if where it takes us. So it didn't take us anywhere. Did I step over that? Yeah, because it was false, so it didn't show. It didn't bring us any code internally. It didn't bring us to any other classes like the integer class. So it's just like, okay, so we're gonna see if just this cast is just casting it to a comparable element. You don't really have to worry about it. So we're just saying, okay, so the target element, which was 30, does it equal the root dot element? Well, what's the root dot element? 11. That's false. So this whole if block gets skipped. Then we're at the else statement. Then we'll say, okay, well, parent points to root. Maybe we will remove the root just to do that shift. After this, so we'll say, okay, parent points to root. Whereas parent, it's null, so we'll step into that. Parent points to the root. Memory location 991. So we'll say, okay, parent points to 991 memory location. So we have target element, which is 30. dot compare to, so we're going to check if it's less than or greater than again. So it's saying, okay, is 30 dot compare to root dot element, which is 11, less than 0? Well, is 30 less than 0? Oh, sorry, is 30 less than 11? That's false. So it's going to return positive 1, not negative 1. So we should skip to here. 30 dot compare to 11. Is that less than 0? It's not, because 30 is greater than 11, so we should skip here. So else, then it's either greater than or equal to, as we said. So if it's not less than, then it's greater than or equal to. So let's put a less than here. Or we don't need to, that's fine. So we'll say result points to. So we have a variable result that's going to save this data here. Is this a recursive method? It might be. I think it is. Yeah, it is, because it calls itself down here, not this part. I don't know if we have enough levels for it to be recursive, but I guess if you have multiple levels, it will be recursive. Hopefully we don't have to do that, so we'll just, because we're just working with a small tree. So we'll say, okay, result points to remove element, we'll pass in target element, which is 30. We're looking for 30. We're going to pass the root to search as root dot, or that param node from which to search, root dot get right, and the parent to the node from which to search, which is parent, which is going to be the root in this case, I think. So we'll step in. Parent points to root, here we go. We'll step in. So now we're in the support method, tResult points to null. If node is equal to null, so what's our node? Our node is our root.getRight. Root get right 1028. Node is 1028, so it's subtree, the root's right child. So if the node is equal to null, that's false. We'll skip. If the target element dot equals, so target element, which is 30, dot equals to node dot element, so it's saying, okay, well, if the target element is 30, does it equal the node, which is the 20 value, the root's right subtree? Well, does 30 equal to 20? No, that's false. Step in, so we'll skip this block here. Well, now we're in the else. So we'll say, okay, well, parent now is going to shift to the node, the current node, which is 20. Parent should shift from 11 to 20. I think you really could have used dot element here, but perhaps it just knows that. So parent points, actually, yeah, you don't need to do that. So parent points a node. Maybe the memory location should be there, but I guess it's showing us a value, because the object's storing the value, right? The element. So here we'll say if comparable of target, so if target element, which is 30, dot compare to node. So it's going to check, okay, well, is 30 less than 20 or greater than? Well, it's not going to be that one, because 30 dot compare to 20 is not less than 0, it's on -1, so it should be this one. it's greater than or equal to, it's greater than or equal to. So we'll say call itself and pass in the node.getRight. So what's the node? It's memory location 1028. We'll say okay, root left child, right child. We went to the right child, 1028. Now it's going to pass node's right child for the node, which is 1046. Excuse me. 1046 is going to be the next node to search, and the parent has shifted to 1028, so it has shifted to the node's parent, and now we've gone into a lower level of the tree, which is 30, because we don't have our tree here, but I think that's it. So there we go. Call itself. It's kind of a recursive, it is a recursive method, but I think it's a simple recursive method because there's no steps after it. So it's just like, okay, keep searching for this method, but there's not any confusing recursion stuff. So it's just like, okay, call itself and keep going down. They could have used a loop too, but I guess they wanted to do it this way. Like, excuse me, when we did find min and find max, remove max and min, we used a loop. We didn't use recursion, but you can use recursion. It's up to you. Loop was easier, it just did it in one couple lines, right? So now we're gonna reset tiers, or yeah, this is gonna be its own data, I guess, for its own recursion. But right now we're gonna reset the variable. So result points to where are we? Results points is not going to show null data. So if the node is equal to null, well, what's our node? Our node should be the 30 node. Right here, 1046. That's where we left off. That's what it passed as the node.getRight. So if node is equal to null, which is false, because node is storing the value we're searching for, 30. So skip. So this one should be true. So if comparable of target element. So if target element, which is, let's remove these watches here. If target element, which is 30, compared to the node get element, which is 30, that's true. So we found the element, we step in. Result points to node.element, so it's going to save the 30. Temp points to replacement, so it's going to call the replacement method. We'll jump into it. Binary tree, so what does replacement do? Returns a reference to a node that will replace the specified one for removal. So right now we're at a leaf, so we really don't need to replace it with anything. If we were in the middle of the tree, we would have to probably replace it to keep it balanced. We'll go over balancing stuff in the next video. So binary tree of generic type T, result points to null. We have a new local result that's set to null. If node.left is equal to null, we still have our this in root. So if node.left, so just on that note, I think in recursion, when you get into passes, recursive passes, the global data, instance data, it stays the same, but the local variables can change for that pass. So you might have to keep track of it as we did before in the previous one of the comparator or something, maybe the sorting methods, those videos. We did some passes. You have to keep track of the data for each pass, so it gets a little confusing. So anyways, if node.left is equal to null, So okay, we'll say, okay, so it's asking for a node. It's checking our node. So the node which points to 1048 memory location, is its left child point to null, or does its left child point to null? Yes, it does. And if the node's right child points to null, so is the node's left child point to null? It does. Here's our node 1048, sorry, not 4846, 1046. Excuse me if I messed that up earlier. Can't see the screen, like the font's so small. So the value, the node holding 30, the left child points to null and the right child points to null. So it's saying, okay, it's checking if node.left points to null and node.right points to null. It does. So it's going to say, okay, well, result points to null. We're going to replace that node with null because we don't need to replace it with anything. We're just going to set it to null. So it's either if, else, if, or else, and then return result. So it's going to be one of these options. We got the first one. So we'll step in. Now we're done with that method. So temp now points to null. It should. Temp's null, you can see that. And we'll say, okay, parent dot right. So if the parent dot right, so it's going to check. So it's going to say, okay, if the parent, which is 20, if its right child is points to node, is that true? So we'll say, okay, parent. So here they're checking by memory location with that equal sign, I think. So we'll say, okay, if parent dot right, parent, which is 1028, dot right, which is 1046. So is the parent dot right's child, does it point to the node? Well, 1046. That's its right child. Does that point to 1046? It does. Then I'll say, okay, parent dot right points to temp. So they're doing a set. They're nullifying here, and they're doing it in a different way. They're saying, okay, well, parent dot right, set it to temp when temps is set to null. So temp really is null, and they're just doing that in the extra step. So parent dot right, which is 30, gets set to null. So parent, which is the node holding 20, its right child, so where are we here? Parent, which is 20. Parent, which is the node at 1028, holding the value 20. Its right child points to, which is pointing to 30, gets set to temp, which is now pointing to null. See? Parent, its right child is gone, points to null, mod count plus plus. And Dawn is going to do the recursive thing. It's going to bounce around with no any further processing. That's where it makes it easy. So this was an easy recursive method, but perhaps if we, I think even if we went down further levels, the way they did it here, it's like an easy recursive method, so we got lucky here. There's no further processing with which makes it confusing. Return result. It says it's done, so 30 should be removed. Tree. So 11's our root, 4 is our left child, 5's our right child, so we'll just check left to see. Left child of that is 2, right child is 5. Null, null, that's good. Null, null. That's good. So then we'll say, okay, root, check the right subtree, the edge of the branch. We'll say, okay. 11 root 20 is right child. We'll say, okay, left is 18. Null, null. That's good. And its right child is set to null. So that's correct. 20, right here. Left child, 18. Which its children are null, null. And right child, which is this one, which was 30, set to null. So I hope that helps. I think I will come back. We don't need to remove any more. Maybe we can actually remove the root, so maybe I'll just put here a note, remove the root. Then we'll be done with the removals. We did replacement, we don't need to do that. We don't need to do this really. We could maybe. Was that the confusing part? Okay, maybe we'll come back and do that. So if node.left points to null, and so we got that one. If one or either of them is null, okay, so maybe if both children are not null, that's going to do a rotation, I think. So we'll come back to that. So we'll test that. We'll remove the root just to do that quickly, and then we'll remove all occurrences. Oh yeah. We'll test that too. And these ones are pretty easy. We just need to do one or the other. So we'll come back and do that.